Supernovas, the sensational and exceptional death of stars, produce the biggest blasts in the universe.
Now, only a small minority of stars actually explode, but those that do just go kablam, blowing themselves to smithereens.
Releasing more energy than the sun does in its entire lifetime by more than 1 billion.
The spectacular detonation blasts vast amounts of lethal radiation into the universe.
If a star at the center of the planetary system would go supernova and explode, it would probably wipe out all forms of life in that planetary system. Radiation would basically sterilize all forms of life on any planet in a planetary system.
Like homicide detectives poring over clues to a cosmic crime, scientists use state-of-the-art tools, telescopes, and technology to find supernovas and to solve the mystery of how and why they occur.
It's an interesting thing because the explosion, the event, has already taken place. And then we get these clues which we gather with our telescopes and try to figure out what happened.
As the stellar investigators know, supernovas have a dual personality. They have absolute power to destroy, and at the same time, they are fundamental to creation itself.
When a supernova goes off, the explosion produces a lot of light, but it also produces heavy elements out of the light ones. So, for example, iron or calcium or sodium or any of the elements of the periodic table, those things came from exploding stars that went off before the sun was formed.
The elements produced in these enormous stellar explosions actually make planets, plants, and people.
The calcium in your bones and the oxygen that you breathe were all cooked up in stars and blown out into space. The shock waves from exploding stars can compress nearby clouds of gas and trigger their gravitational collapse so that they begin the renewed process of formation of new stars, planets, and ultimately life.
Thanks to circumstantial cosmic evidence collected, experts estimate that a mighty supernova goes off somewhere in the universe once every single second.
So that's something like 30 million per year, and that's been going on for the last 10 billion years or so of the universe's existence.
Giving us a sense of how big the universe is, in a typical galaxy like our Milky Way, a supernova suddenly occurs only once or twice a century. However, nobody knows when the next one might come.
It's a completely random process, so we have no idea when the next one will occur. It could be tomorrow, could be 5 minutes ago, could be another 100 years. We don't know.
If it is very close, you would see a very bright event in the sky. It could be even brighter than the Venus or the planets or even the moon or maybe even the sun if it's bright enough.
If a supernova is too close to you, it can definitely destroy life. The flash disrupts the atmosphere, burns things up.
Astronomers are constantly policing the skies, keeping a wary eye on at least 2 stars in the Milky Way that have the potential to catastrophically explode close to Earth. One that threatens to blow lies in the heart of the Eta Carina Nebula, about 9,000 light-years away.
Eta Carina is one that we know about, which is a very massive star, maybe even 100 times the mass of the sun, has a very short life, and it could be that the end of that life will take place sometime very soon.
Another star in danger of going supernova is Betelgeuse, a star in the Orion constellation. This seething star is 15 times the size of the Sun. This one is even closer than Eta Carina to Earth.
It's roughly 500 light years away. It'll be a spectacularly brilliant sight, visible even in the daytime.
There's no question Betelgeuse is going to blow up. It could be tonight, for all our ignorance. It could be 10,000 years from now, short on an astronomical time scale. But it could be tonight that we're sufficiently ignorant about it. So it is worth looking at every night to see whether it's blown up.
Not only do the massive supernova explosions create and destroy stars, planets, and people, they also unleash powerful energy in the form of cosmic rays. These highly energetic charged particles strike our planet each and every day. What's more, they have the capacity to alter evolution.
We live in what I call a disturbed galactic ecology. It is a very eruptive, energetic galaxy out there, and our planet is going to get pummeled by that stuff.
Experts say they can and do change life as we know it.
Well, we know that there are genetic mutations that take place when cosmic rays hit living things. It disrupts the DNA inside cells. And if there were a supernova nearby, there could be a lot more cosmic rays, like 100 or 1,000 or 1,000,000 times more than we ordinarily get. If you're the old species, it might lead to your demise, but it also might lead to new species being developed. So a supernova could be an agent of change, and it could be for better or for worse.
Knowing that supernovas have the power to create and alter life makes it imperative that humankind unravel the riddle of what makes these stellar time bombs tick.
What have you got here?
All right, so this is the supernova factory supernova.
The key to unlocking the mystery lies in the detailed analysis of what is ejected into the cosmos by a supernova.
I'm glad this one did not escape our attention because it was a winner.
Yeah.
It's a great supernova.
Nature has given us this puzzle. It says, well, I make these objects easily, and we as theorists have to figure out how nature does it.
11825, code 6, 105 North Avenue.
As with any crime scene, critical clues are contained in what is left behind. Like a gunshot, hot gases and explosive debris are propelled through space by these deadly stellar explosions.
Just as these gunshots are driving a shock wave, and you can hear this strong noise from the shock wave, it's actually compressing the matter and heating it up. Shock wave in a supernova is doing the same thing.
As these pieces of shrapnel are hurtling very fast through space, they collide with the material around it, and what forms is a shock wave.
The fantastic stellar detonation shoots vast amounts of ballistic supernova evidence, cosmic debris called remnants, into the universe.
So the remnants are produced as this shock wave keeps on moving out through the universe. It actually produces this very picturesque image of the shock moving outward.
The gases that made up that star are ejected at tremendous velocities, 10,000 miles a second, and so they create an expanding shell, and eventually that can become very, very large.
These things go for thousands of years or even tens of thousands of years. So sometimes we can see the site of a supernova explosion tens of thousands of years after the event has taken place.
The high-speed collision of stellar debris in the shockwave produces intense heat and light in wavelengths invisible to the human eye. They include radio, infrared all the way to X-rays, and gamma rays. Fortunately for astronomers, sophisticated space-based instruments like Hubble, Spitzer, and the Chandra X-ray telescope can help the cosmic detectives see them all.
So basically every instrument in every way you can gives you a somewhat different perspective on what's going on, and then you try to put all that together as an intellectual enterprise.
Like a fingerprint, each supernova has a unique pattern, and they can be analyzed in several different ways.
One thing we can do is measure how bright the supernova is, and that's what we call the light curve. The other thing that we can measure that is really helpful is what we call the spectrum. We take the light from a supernova at a telescope, spread it out into a little rainbow using a prism or a grating, and then measure how much light there is at each color or wavelength.
Analysis of that line can tell us lots of interesting things, like the chemical composition of the supernova, the temperature, the pressures and densities of the gases, how quickly they're expanding, and so on.
Information gleaned from the light curve and spectrum reveals distinctions between each supernova.
So it is much like a detective job where you get different clues from the light curve or from the spectrum and try to figure out what kind of star it was, what made it explode, what the products of the explosion were, and what the effects of that explosion might be.
As time goes on, we can see deeper and deeper into what the star originally was, so we can actually get what the composition of the star was at the time it exploded.
By comparing the light curves and spectra from literally hundreds of supernova cases, scientists have been able to classify supernovas into two main types. Type 1A supernova release no hydrogen. The explosions are uniform in size and luminosity. Type 2 supernova release large amounts of hydrogen. The explosions vary greatly in size and luminosity. But why would there be such distinct types of exploding stars? Might they be blowing themselves apart in different ways? Scientists focused their efforts on uncovering the mammoth question: what drives these stellar monsters to destroy themselves?